What are the laws of physics? They are the fundamental rules that govern our universe. Think about gravity. It is a law. It keeps your feet firmly on the ground. It holds the moon in orbit around the Earth. It keeps the Earth circling the sun. This law seems to work everywhere we look. It works today, just as it did yesterday. We expect it will work tomorrow too. This idea of constancy is incredibly powerful. It allows us to make predictions. It lets us understand the world around us. From the smallest atom to the largest galaxy, these rules seem to apply without exception. They are the invisible architecture of reality itself. We see these laws in action all the time. When you throw a ball, its path through the air is predictable. We can calculate its journey because we understand the laws of motion and gravity. The speed of light is another one of these great constants. It is the cosmic speed limit. Nothing with mass can travel faster. This rule underpins so much of modern physics, including Einstein's famous theories of relativity. These laws are not just ideas, they are descriptions of how the universe behaves. They are consistent, reliable, and universal, or so we have always assumed. They are the silent partners in every event that has ever happened. The idea that these laws are fixed is a cornerstone of science. It means that an experiment performed in London today should yield the same result if performed in Tokyo next year. It also means that the light from a star a billion light years away obeyed the same rules when it began its journey as it does when it reaches our telescopes. This assumption is called the principle of uniformity. Our journey into the history of physical laws begins in ancient Greece. Early thinkers like Aristotle looked at the world and tried to make sense of it. They saw two distinct realms. There was the earthly realm, right here beneath our feet. Things here were messy, chaotic, and temporary. A dropped stone falls to the ground. A fire burns out. But when they looked up at the heavens, they saw something entirely different. The sun rose and set with perfect regularity. The moon went through its phases with predictable grace. Then came Isaac Newton. He was the figure who truly unified the heavens and the earth. The force that made an apple fall from a tree, he reasoned, was the very same force that held the moon in its orbit around the earth. Newton formulated his ideas into precise mathematical laws. His laws of motion and the law of universal gravitation could describe the flight of a cannonball and the orbit of a planet with the same set of equations. In the 19th century, scientists like Michael Faraday and James Clerk Maxwell worked to understand the mysterious forces of electricity and magnetism. They discovered that these were not separate phenomena, but two sides of the same coin, electromagnetism. Maxwell captured their behavior in a set of elegant equations. These equations showed that light itself was an electromagnetic wave. Scientists uncovered the laws of thermodynamics, which govern energy, heat, and entropy. They described the inevitable flow of energy from orderly states to disorderly ones. The picture of an orderly cosmos grew clearer and more detailed. The assumption of constancy was more than just a scientific principle. It became a philosophical one. By the end of the 19th century, the Newtonian model of the universe seemed almost complete. It was a magnificent clockwork running with perfect precision according to fixed, eternal laws. Scientists felt they had uncovered the fundamental principles of reality. It felt like the final chapter in the story of physics was about to be written. But a few stubborn problems remained. They were like tiny cracks in a perfectly polished mirror. One of these problems was the orbit of the planet Mercury. It didn't quite follow the path predicted by Newton's law of gravity. Astronomers tried to explain it by hypothesizing a hidden planet, which they named Vulcan, orbiting even closer to the Sun. But despite years of searching, Vulcan was never found. The anomaly refused to disappear. An experiment by Albert Michelson and Edward Morley in 1887 was designed to detect this ether wind. They measured the speed of light in different directions, expecting to find a slight difference. But they found nothing. The speed of light was the same, no matter which way they looked. These were not just small technical puzzles, they were deep, fundamental contradictions that struck at the heart of classical physics. The perfect clockwork universe, so confidently assembled over 2 centuries, was beginning to show signs of stress. The rules that seemed so universal and unchanging were failing to explain observations at the edges of their domain. These small cracks were about to be pried open. leading to a revolution that would completely reshape our understanding of space, time, and gravity. The person who shattered the old clockwork model was a young patent clerk in Switzerland named Albert Einstein. He was deeply troubled by the contradiction between Newton's ideas and Maxwell's equations. What if the speed of light was not just constant, but constant for all observers, no matter how fast they were moving? In 1905, he published his theory of special relativity. It showed that space and time were not absolute and separate, as Newton had believed. Instead, they were interwoven into a single fabric space-time. According to Einstein, an observer's motion could stretch time and shrink space. Two events that seemed simultaneous to one person might happen at different times for another. The universe was not a fixed stage on which events unfolded. The stage itself was flexible, dynamic, and relative. But Einstein was not finished. He spent the next decade wrestling with gravity. A massive object like the sun creates a deep curve in space-time around it. The Earth isn't being pulled by the sun, it is simply following the straightest possible path through this curved space-time. This was his general theory of relativity, published in 1915. It explained the wobble in Mercury's orbit perfectly. The planet was moving through the deeply curved space-time close to the sun. In 1919, during a solar eclipse, the astronomer Arthur Eddington photographed the stars near the sun. He found that their light was indeed bent as it passed by the sun, exactly as Einstein had predicted. The revolution was complete. The law of gravity had not changed over time, but our understanding of it had been completely reborn. At the same time that Einstein was rewriting the laws of the cosmos, another revolution was brewing in the world of the very small. They found that energy did not seem to be continuous. Instead, it was emitted and absorbed in tiny, discrete packets, which Max Planck called quanta. It was as if you could not pour water smoothly from a jug, but could only pour it out in individual identical droplets. In the quantum realm, a particle like an electron does not have a definite position or a definite speed until you measure it. It exists in a haze of possibilities, described by a wave function. The laws of this world were not deterministic like Newton's. They only gave you the odds. You could calculate the probability of finding an electron in a certain place, but you could never know for sure where it would be. Einstein famously hated this idea, declaring God does not play dice. But experiment after experiment proved him wrong. The quantum revolution gave us a new set of fundamental laws. These laws governed the behavior of atoms, photons, and all the subatomic particles. This created a new division in physics. We now had two sets of incredibly successful laws. General relativity, which described the universe on the largest scales of stars and galaxies, and quantum mechanics, which described the universe on the smallest scales of atoms and particles. The problem is that these two sets of laws are mathematically incompatible. They are based on different principles and speak different languages. So how can we possibly test if the laws of physics have changed over billions of years? Well, we cannot build a time machine and travel back to the early universe to run experiments. But, we have something almost as good. We have light. Light travels at a tremendous but finite speed. This means that when we look out into the depths of space, we are also looking back in time. The light from our sun takes about 8 minutes to reach us. So, we see the sun not as it is now, but as it was 8 minutes ago. Astronomers use powerful telescopes to look at galaxies that are billions of light years away. The light from these distant objects began its journey long before the Earth even formed. It has traveled across the expanding universe for eons, carrying with it a snapshot of the physical laws as they were in that ancient epoch. This light is our cosmic time machine. It allows us to be cosmic archaeologists. We can analyze this ancient light and compare the physics of the distant past with the physics we measure in our laboratories today. We are looking for changes in the fundamental constants of nature. These are the special numbers that underpin our physical laws, like the speed of light, c, the strength of gravity, g, or the charge of an electron. To do this, astronomers point their telescopes at quasars. Quasars are incredibly bright, active cores of very distant galaxies. They are so bright they act like cosmic lighthouses, shining across billions of light years. As the light from a quasar travels towards us, it often passes through vast clouds of gas in intervening galaxies. The atoms in these gas clouds absorb some of the quasar's light at very specific frequencies, creating a pattern of dark lines in the quasar's spectrum. This pattern is like a barcode. It tells us which elements are in the cloud, and it encodes the value of the fine structure constant at that location billions of years ago. In the late 1990s, a team of astronomers in Australia made a startling claim. They had analyzed the light from dozens of distant quasars. Their results seemed to show that the fine structure constant was slightly smaller in the past. The change was tiny, just a few parts per million, but it was consistent across many different observations. This was a potentially revolutionary discovery. It sent ripples of excitement and skepticism through the physics community. Other teams of scientists, using different telescopes and different analysis techniques, set out to verify or refute this result. While astronomers look to the distant cosmos, there is another remarkable place we can look for changes in physical laws right here on Earth. It is a place called Oklo in the nation of Gabon in West Africa. In 1972, French scientists analyzing uranium ore from a mine in Oklo found something very strange. After ruling out all other possibilities, they came to an astonishing conclusion. The uranium deposit at Oklo had once been a natural nuclear fission reactor. The remains of this 2-billion-year-old reactor provide a unique laboratory for testing the constancy of physical laws. The analysis is incredibly complex, but the overwhelming consensus is that the data is consistent with no change. The nuclear reactions that took place deep underground 2 billion years ago appear to have followed the exact same rules that govern our nuclear power plants today. This result from our own planet stands in tension with the tentative hints of change seen in the light from distant quasars, deepening the mystery and making the ongoing search even more compelling. The debate is far from settled. These measurements are pushing the limits of our technology, and the search for a definitive answer continues to be a major driver of modern cosmology. It turns the entire observable universe into a giant laboratory where we can test the constancy of nature's laws across cosmic history. The debate over changing constants highlights just how special our universe appears to be. This is often referred to as the fine-tuning problem. The fundamental constants of nature have values that seem to sit on a knife edge. If you were to nudge their values even slightly, the resulting universe would be unrecognizable and almost certainly lifeless. For example, if the strong nuclear force were just a tiny bit weaker, protons could not stick together, and the only element in the universe would be hydrogen. This delicate balance is one of the deepest mysteries in all of science. Why do the constants have the specific values they do? Let us now imagine, just for a moment, a universe where the laws of physics are not constant. What would this truly mean for science? Well, the immediate consequence would be a profound crisis for our ability to predict the future. But if the fundamental constants, like the strength of gravity or the charge of an electron, were, slowly but surely changing, then all of our predictions would suddenly carry an expiration date. This would force us to rewrite our most fundamental theories. Newton's laws, Einstein's relativity, and the standard model of particle physics. They're all built on the bedrock of unchanging constants. Our entire technological civilization is, in a way, a tower built on the foundation of physical constancy. If that foundation proved to be unstable, the whole structure would be at risk. Discovering that the laws of physics evolve would do more than just change our science and technology. It would profoundly alter our philosophical perspective and our sense of place in the universe. But if the laws themselves can change, it would mean we are living in a more provisional, temporary kind of universe. The cosmic rules that allow for our existence might just be a feature of the current epoch, a fleeting moment in the grand timeline of reality. It would encourage us to cherish our fleeting moment in the cosmic sun, a time when the laws of nature have conspired to allow for stars, planets, and conscious beings who can ponder these very questions. This journey into the heart of physics ultimately leaves us with a profound sense of humility. We stand before the universe like a child on the shore of a vast and unexplored ocean. What we have learned is immense, a testament to human curiosity and intellect. We have mapped the cosmos, decoded the language of light, and uncovered the rules that govern atoms and stars. Yet the ocean of what we do not know remains boundless. The existence of dark matter and dark energy, the incompatibility between our theories of the large and the small, These are stark reminders that our current map of reality is incomplete. The question of evolving laws fits perfectly into this context of mystery. It represents one of the great known unknowns at the frontier of our knowledge. To even be able to ask such a question is a remarkable achievement. It means we have a physical framework so robust that we can test its own foundations across billions of years of cosmic time. But the fact that we do not have a definitive answer yet is deeply humbling. It tells us that for all our progress, we are still just beginning to grasp the ultimate nature of the universe. This humility is not a cause for despair, but a source of inspiration. It is the engine that drives science forward. The search for answers continues. New telescopes, new experiments, and new minds will take up this challenge. Perhaps one day, we will know for sure whether the cosmic rulebook is written in permanent ink or erasable pencil. But until then, the uncertainty itself is a gift. It keeps the universe interesting. It keeps the story of science alive and full of suspense. And it reminds us that the most exciting thing about our cosmos is not just what we know, but everything we have yet to discover. The journey is far from over. In fact, it may have only just begun.